Lesson 2.5 is titled Completing the Square. In this lesson, we'll look at quadratics that are perfect squares, and then we'll look at quadratics that we can make into perfect squares. A perfect trinomial square is any quadratic equation that can be written as the product of two parentheses that are the same. We remember seeing that in vertex form. Over on the right, it says circle the quadratic functions that represent, or should say that represent, perfect trinomial squares. Well, to figure out whether or not this works, we're going to have to factor. And that's something that we talked about in the last chapter. X squared minus 4x plus 4. When we first look at that, we have to recognize that the a value is 1, so that's good. We'll then split apart the 4. We know 4 can break down into 1 times 4 and 2 times 2. Now we need to figure out how to multiply those two pairs, or those two values, to get positive 4, but then when we add, they have to get negative 4. If you're thinking negative 2 and negative 2, that would be correct. This means we'll split our x squared up into x times x, and then we have minus 2 and minus 2. That means it can be rewritten as x minus 2 squared, since the parentheses are the same. This is an example of a perfect square trinomial. You guys try the next one. Take x squared plus 10x plus 25 and factor it, and see if you can determine whether or not it is a perfect square trinomial. For the x squared plus 10x plus 25, I recognize that 5 and 5 would multiply to get 25, but add to get positive 10. Therefore, this is also a perfect trinomial square. If we try the next one, x squared minus 3x plus 9, 9 can be broken down into 1 times 9 or 3 times 3. And we need to get, that's a comma right there, and we need to get negative 3 in the middle. This one doesn't factor. We can't figure out which pair would get positive 9 when you multiply and negative 3 when you add. So this is not a perfect square. Oh, that was my attempt at drawing a square. Sorry. Let's try that again. That's better. Okay, trinomial. Oh boy. All right, the last ones. We saved the best one for last, of course. Need a little bit more room on this side. The last one, if we try to factor, recognizing that a value now is 4. Okay, hang on. Sorry about that. I had to open up the door for my cats to look outside and watch the birds. So now we're back. Okay, if we have that 4 out in front, we have to do the a times c rule. 4 times 9 is positive 36. Now, we have lots of factors for 36. We could use 1 and 36, 2 and 18, 3 and 12, oh boy, 4 and 9, and 6 times 6. So there's lots of choices for this one. We want positive 36 when we multiply, but negative 12 when we add. Taking a look at those 5 options, it looks like negative 6 and negative 6 are going to be the pair that works. But remember, when we factor using that a value out in front, we now have to do 4x squared. And then on the inside, we have to do that split the b rule. We haven't done that in a while. So we'll say minus 6x minus 6x. That splits the b in the middle, and then plus 9. And we'll group. Hopefully this sounds familiar to you guys. In that first parenthesis, we have 4x squared minus 6x. We could take out a 2 and an x, and we would have 2x minus 3 left over. In that next parenthesis, negative 6x plus 9, we have to take out that negative to keep that first term in the parenthesis positive. And what could we take out of 6 and 9? We could take out a 3. If we factor negative 3 out of negative 6x, we would get positive 2x. And if we factor negative 3 out of 9, guess what? We get negative 3. Our parentheses match. That means that's one factored answer. I'm just moving it down here so I have more room. And then the parts on the outside, get this, are the same thing, 2x minus 3. Voila, guess what? We have a perfect trinomial square. You can rewrite it as 1 parenthesis being squared. So 3 out of the 4 were perfect squares. Well, thinking about the one that wasn't, there's got to be a way to do some work with those terms to create a perfect square. And that's called completing the square. This is going to be quite the process. Please make sure to carefully write down these 5 steps. We'll start the complete the square process when a equals 1. You'll end up with a quadratic x squared plus bx plus c. The first thing you'll want to do is set your quadratic equal to 0 and then move that c value over to the other side. Then take half of the b coefficient and square that answer. Once you get that number, add that number to each side. The quadratic then will be able to be factored and written as a perfect square. Let's try a couple of examples. It says convert f of x equals x squared plus 8x plus 5 to vertex form by completing the square. So currently, our function is in standard form. And what we'll do is we'll follow the complete the square process and write it in vertex form when we're done. Step 1, set the equation equal to 0. X squared plus 8x plus 5 equals 0. It then says move c to the other side. If c is positive, we'll subtract 5 to move it over. And then we get x squared plus 8x on the left is equal to negative 5 on the right. That's step 1. Step 2, take half of the b coefficient. So half of that b value. Half of 8 is just 4. And that's all you do in step 2. That's not bad. Step 3, square that answer. 4 squared is 16. Step 4, add 16 to both sides for the equation, in the equation. We have x squared plus 8x. I'll add 16 on the left. We had negative 5, and we'll add 16 on the right. We add the same thing to both sides of the equation to keep the equation balanced. On that left-hand side, we now have a perfect trinomial square. If we think about numbers that multiply to get 16 but add to get 8 in the middle, that would be positive 4 and positive 4. X plus 4 and x plus 4. Here's something to note. We saw 4 in step 2, and it was positive. That 4 is always going to match in our factored answer. It's kind of nice that way. Oh, wait a minute, we're in step 5, aren't we? So we know that's true. On the right, negative 5 plus 16 is positive 11. Now remember, we're supposed to write the 2 parentheses as a perfect square. X plus 4 squared is equal to 11. So this is completing the square. We're done with that part of the process. However, we were asked to write in vertex form. All we need to do now is make sure it follows our vertex form template. And that was y equals, or f of x equals, a times x minus h squared plus k. Well, we've got the x minus h squared part. We just need to move the 11 to the other side for that plus k part. So if we do x squared plus, well, not that at all. Hang on. Here we go. If we do, sorry about that, if we do x plus 4 squared equals 11, we'd have to move 11 back over by subtracting. That won't go on the inside of the parenthesis. We have to be careful with our order of operations. That would go after, and that's like the k value. In vertex form, this will be our final answer now. We would write f of x equals x plus 4 squared minus 11. So that's converting from standard form to vertex form of a quadratic function by completing the square. Another purpose for completing the square, we can actually solve an equation by completing the square. To do that, we'll complete the first 5 steps up above for completing the square. Then what you'll do, instead of moving the k value over to convert to vertex form, you'll take the square root of each side and then simplify. So that's another option where completing the square would be useful. Let's put that to the test. How can you solve 0 equals x squared minus 2x plus 3 by completing the square? If we follow those first 5 steps, the first thing you want to do is set it equal to 0, and it already is, so we're in great shape there. And we'll move c to the other side, so we'll subtract. Now we end up with x squared minus 2x equals negative 3. That's step 1. Step 2, take half of that b coefficient. So this is important right here. B is actually negative 2. Half of negative 2 would be negative 1. In step 3, if you square negative 1, we get positive 1. So just be careful on watching those particular details. And then we add that to each side. We get x squared minus 2x plus 1 on the left, negative 3 plus 1 on the right. Step 5, factor your trinomial. If we want 2 numbers to multiply to get 1, but add to get negative 2, that would be x minus 1 and x minus 1. And remember, we talked about that up above. That comes from that part or that answer in step 2. It's always the exact same factor. It's nice to have that consistency at least. And then on the right-hand side, we have negative 3 plus 1, which is negative 2. And then we'll write our perfect trinomial square as a product or as a perfect square. X minus 1 squared. So there's our first 5 steps. We'll get pretty good at that by the time we're done with all of these options. But if we're asked to solve, what we'll do is we'll take the square root of each side. So we'll start with x minus 1 squared equals negative 2. I'm going to put that dot there. And then we're going to square root each side. And remember, the square root cancels out with the perfect square, and that'll give us x minus 1. On the right, remember what we talked about the other day. If you take the square root of a number, you must put plus or minus out in the front. And then we have the square root of negative 2. Well, this should indicate something to us right away. With that negative on the inside, this is going to be a complex solution, not a real solution. And we're going to factor out that negative, whoops, hang on, by putting an I out in front, but it won't go in front of the plus or minus. It goes right in front of the square root. And then the 2 is positive on the inside. Trying to simplify 2, the only numbers that go into 2 are 1 and 2, and 1's a perfect square, but it won't help us simplify. So this is already simplified, which again, kind of nice. So now if we're trying to solve for x, and we want to get x by itself, we would have to add 1 to the other side to move it over. Thinking about order of operations, that 1 is going to go in front of the plus or minus, because we could add or subtract that second part. So there are technically 2 complex solutions, or 2 imaginary solutions. It'd be 1 plus I radical 2 and 1 minus I radical 2. And this is the first part of lesson 2.5.